All right, hello everyone, and sorry, I think it's working. Is it okay? Oh, I see, sure, perfect. All right, great. Yeah, so I am Kevin Hayes. I work out of Mount Royal University. We're doing what we think is some pretty interesting stuff with some aircraft engine oils. We take a little look at them with a bunch of different analytical techniques, but one of those techniques that we like to use is GCGC. So first, I'll give you just a little bit of background. We'll start with aircraft oils. They're relatively complex. There's a bunch of different brands, a bunch of different manufacturers, and they make oils for a bunch of different engine types, right? So there's all different types of aircraft. There's piston engine aircraft all the way up through jet aircraft, and the oils vary in terms of kind of their base type and their complexity, and what kind of additives go in them. For a piston engine aircraft, for example, you'd see maybe a mineral oil base, whereas if we go to a jet oil, we're looking at esters of pentetherols, a bunch of different organophosphate additions to make sure that they can handle the high temperatures and high pressures that are associated with it. To add to that very slightly, there's also aftermarket additives that can potentially come into play. So these aftermarket additives could be recommended by manufacturers. That could be even kind of required to be put in by airworthiness directives from the FAA or other groups. When we were doing our sampling, we looked at a bunch of different aircraft types, so I thought we'd just briefly touch on the engines because they're fairly important. We got oils from jet aircraft as well as turboprop and piston engine aircraft. They are similar in a lot of ways. The main kind of similarity is that they all provide thrust for the aircraft. At some point, they allow the aircraft to fly, but they do have some major differences as well. Some of the differences go in with how they're fueled. So jet and turboprop aircraft, they're going to use jet fuel. In US, it's mostly Jet A. In other places, Jet A1 is often used. These are kerosene-based fuels. If you go to really cold places like northern Canada, you can see Jet B. This would be a naphtha-based fuel. So there's differences in fuels. There's the differences in oils that I mentioned before. There's also differences in what's actually in the engines themselves, right? So the things that make them up. In the turboprop and the jet engines, there's lots of superalloys, so alloys of steel that contain molybdenum, nickel, all kinds of different things. When we go to piston engine aircraft, that's not the case anymore. There's no real need for those superalloys. They're fueled with avgas. I don't want to put the cart before the horse or anything because we're going to talk about that. That's one of my big reveals later in the talk, but so we'll save that for a little bit later. But they're quite a bit simpler. They don't have the temperature requirements, and as I mentioned before, there's mineral oil is their kind of base stock for their oil. So the purpose of our study was we wanted to figure out kind of what was happening with these oils with use. So a lot of the research that's gone on so far about this place, or this space I should say, has basically involved either new oils without really assessing the used oils after use, or has involved looking inside the aircraft cabin at the oils that have made their way kind of from the engine into the cabin via the bleed air pathway. So jet and turboprop engines definitely have this possibility that oils can make their way into the cabin. That's less common with piston engine oils. So what we really wanted to see was whether we were losing compounds from our oils with use, and if we had those lost compounds, whether or not those compounds were potentially making their way into the cabin. We also wanted to see if the oils were accumulating anything with use. We wanted to see if they're picking anything up from kind of a occupational health and safety perspective. So if individuals were kind of coming into contact with these used oils, let's say maintenance personnel or something along those lines, if they're coming into contact with something that was potentially harmful for their health. We had a good starting off point to kind of go with. The routine elemental analysis of oils is done regularly. It's done typically from a maintenance perspective. So this is done, let's say you have your aircraft, you'll take a sample of oil, you'll ship it off to the lab, and they'll come back and say, oh, your oil is high in aluminum or something along those lines. It's a good idea that you check your pistons for wear. And so it's a maintenance kind of scheduled choice that helps make sure that the aircraft remain airworthy. We decided to take it a step further and start looking at compounds, or I guess in this case elements that would exist in additives and things like that that wouldn't typically be tested for. So in our study for our elemental analysis, we gathered a bunch of oils. We were fortunate. The university that I work at has a aviation department, and they were kind enough to donate some used oils with the regular maintenance of their small aircraft fleet. So those are some of the planes there that we got some oil from the piston engine. They also kind of leaned on some partners at the airport to get us some turboprop oils. Jet oils are incredibly hard to come by. Used jet oils are incredibly hard to come by. We were able to source a few from a business jet company out of Europe. If anyone has an in, please let me know at some point during this conference. I desperately need more samples. But we were able to do that. We sourced these samples, and then we injected them into an ICP OES, or inductively coupled plasma optical emission spectrometer, or spectroscope. Sorry, I don't know. Anyway, we put it in, and we took a look at some of the results. So I have some kind of interesting results that we start with. This is our analysis of wear metals, so this would be the equivalent of the routine analysis. What you see here in the yellow, that's our fresh oil. So you can see it has basically none of the metals or elements that are in there, which is expected because there has been no wear to date. And then as you move along, the x-axis there, you see a bunch of different aircraft type. We see in these piston engine oils increases in iron and nickel. This is kind of expected stuff. We do see some elements that could potentially be slightly problematic for people who are handling the oils, like we see increases in cadmium and things along those lines. But we don't know anything about the species or anything along those lines with these elements at this point. When we look at our jet and turboprop oils, we also see some wear elements, much less. There's no piston in a cylinder, so less kind of friction and things along those lines. But we still see kind of things like molybdenum and some of those things that are associated with the superalloys. Where it gets a little bit more interesting is when we start to look at those elements that weren't in the routine analysis. So this is an example from our piston engine aircraft. We see some interesting stuff. We see increases in sulfur. More sulfur is permitted in aviation fuels than in kind of your typical fuels, so that's not entirely unexpected. What was a little bit unexpected was we found a bunch of lead. I'm not talking a little bit of lead. We found over 6,000 milligrams per kilogram of lead in each of our samples. Anyone have a stab as to why that might be? I guess I'm the talker. Avgas. Avgas is leaded. It's one of the only kind of fuels that is still kind of used in North America and elsewhere that still incorporates tetraethyl lead in terms of some of its components, which is it's an anti-knocking additive. And so we found this huge amount of lead. So we decided to look at it compared to the avgas. And we actually have 7 or 8 times more lead in our oils than we have in our avgas. Right? So the oils are actively accumulating some of that lead. Something else that was interesting, you can see it on the last 2 samples there, is we found some phosphorus. The phosphorus, we didn't really know where this is coming from in the sense that there's no kind of fuel source. There's no oil source. We figured it had to be an additive, so we'd look for that later. When it comes to our turbine and our jet and our turboprop engines, what we mostly noted was a decrease in the amount of phosphorus. So I mentioned before, with some of these aircraft, well, especially jet and turboprop aircraft, they're going to be using oils that have organophosphate additives. So we were expecting organophosphates there. But then with use, we started to see that number drop off quite a bit. Right? And that's kind of an interesting thing to look at. Okay. So what this gave us was a kind of possible potential for occupational risk. From our piston engine oils, we have kind of 2 main things. We have the lead. Right? The lead being there, we don't know what species that lead is, right? We don't know if it's still tetraethyl lead, if it's all been kind of degraded and oxidized to lead oxide, or something in between, right? And that could make a big difference if it's on someone's hands during an oil change, especially since the tetraethyl lead has been demonstrated to be able to kind of move through the skin quite a bit easier than our inorganic leads. We also have that phosphorus. We were looking at 600 ppm, give or take, of phosphorus. Depending on the compound, that could be potentially problematic, or it might be no big deal at all. And then we have the jet and turboprop oils, and that's where our main concern there is the loss of that phosphorus. Okay, so The loss of phosphorus with use could be concerning for a couple of reasons. The first one being that phosphorus is in that oil for a reason, right? It's supposed to be in there. It does a lot of really important things for making sure that oil stays stable at high temperatures. The other thing is that that phosphorus could then potentially be becoming available to the bleed air pathway. Right, so two things that we need to kind of look at. That's compounded a little bit by the fact that, especially in large jet aircraft, I don't know if y'all recognize, but they don't really do oil changes so much. The oil burns off at such like a high attrition rate that they can just kind of perpetually add. So to see like the value go down substantially is something that is kind of outside the norm. So we decided to figure out what these kind of compounds were using GC. Yeah, it's a pretty simple method. We diluted the same oils that we were looking at before in hexane, cranked up the split ratio, and injected them. Just trying to make sure that we could see what we were doing. We had an Agilent 7890, GC, an Insight flow modulator, and a benchtop select mass spectrometer. We were operating in only hard ionization mode, so just 70 eV because we thought at least we knew what we were looking for. Okay, so in terms of some speciation results, when we look at the jet and turboprop oil, sorry, this is jet on this side and turboprop on the other side, the only organophosphates we found in there was tricresyl phosphate isomers. We got really good separation, which is nice. We were able to identify with standards our trimetaphosphate and our triparaphosphate. There are a few peaks in there that we don't know yet. They're going to be TCP isomers. We're fairly confident that they're going to be the trimeta-meta-para isomer and the trimeta-para-para isomer of TCP. What we're hoping to avoid and what we need to do some more work in looking at is making sure that there's no orthoisomers present. The orthoisomers of tricresyl phosphate are known neurotoxins. They're actually responsible for some sincere kind of mass poisonings around the world, including one in the United States here during Prohibition called Jake Leg syndrome, sorry. But the important part is that we see here it's only these OPs that are present in these are the only OPs that are there, so we know that the losses that we're seeing in our elemental analysis have to be coming from these molecules for the most part. Something else that's interesting, and I'm just going to touch on this really briefly because we haven't done all the work yet, is so the top and bottom there are new oil samples, and in the middle we have our used oil sample. So what we're seeing is a huge amount of increase in complexity, a bunch more peaks that are showing up in our used oil, especially in the first half of the chromatogram, that we haven't fully explained yet. We think they're degradation products and pyrolysis products of our pentaethertol esters, but we need to look at that in a little bit more detail in the future. All right, let's go into the lead stuff. So for anyone wondering, tetraethyl lead pops up in your chromatograms in beautiful peaks. It is, for its like location in your chromatogram, basically one of the best peaks I've ever had to work with because you're never going to confuse it with anything else because it's so early because it's got a low boiling point, but its structure is just so different. So when you look at the mass spectra, you have your molecular ion and then you just have lead like losing ethyl groups in these really, really defined peaks. So it's super, super nice. It's super, super easy to find. It really sticks out for its boiling point. I raise that to say that when we looked at all our oils and we looked for the tetraethyl lead, there was none. Right? There was a peak that aligned with our retention times, first and second dimension, pretty closely, but we didn't see any of the spectra for that peak that looked like the tetraethyl lead. That's a good thing for the most part. It means that probably for the mechanics' hands and skin are not dosing themselves quite as much with lead, which is super, super important. We think that this probably means that all that tetraethyl lead is being thermally degraded during combustion, and we just have lead oxide left over, and then that just accumulates in the oil over time. So it's good. It's still toxic, but it's good. It's better. In terms of the phosphorus in our piston oil samples, when we looked, we thought that we would see TCP. Okay, so I don't know if it's just me or maybe it's a personal bias or something, but when you work in aviation for a while and you're working with the lubrication, everything is tricresyl phosphate. It just becomes the only thing that you think about or know about. I looked up some of the additives that would be potentially in this piston engine aircraft, and we didn't find, I found some additives that contained a bunch of TCP, so I was pretty sure. We have the standards. I was like, okay, let's run these oils, confirm the TCP, and then I've got a good ending to my talk or whatever I want to do with this. But when I looked, it wasn't TCP. So we found triphenyl phosphate up on the top left, which is something that's not unknown to be in some of these additives. And then we found a little bit of a weird one. In the first dimension, it aligns very closely with where TCP would be, but in second dimension, it's dropped down quite a bit. If you were an analyst just looking at this from a 1D chromatogram, it's highly likely that you would probably chalk this up to be TCP and just move along. Or maybe that's just me with my biases towards that particular compound class. But we think, we don't know, we haven't confirmed it with standards, but we think that it's a tert-butyl phenyl diphenyl phosphate. We don't know exactly what additive this comes from yet. It's still, again, one of those things that's not really great for people, but it's not necessarily as bad as some of those TCP isomers. So that's probably a good thing from an exposure perspective as well. Okay, so overall, basically what some of this work shows is that the aircraft engine oils change quite a bit. They don't stay chemically static during service. During normal operations, we have accumulations and we have losses from the oil. So I guess the important thing to note here is like the oil that an individual might be working with isn't necessarily the same as the oil that's on the safety data sheet, right? It's something that's a little bit different. Using our elemental analysis gave us a useful kind of first look at what we could look for the patterns, but getting down to the compound level with GCGC and having that resolution, the resolution power to kind of separate out the things that we were looking for really played a major role in kind of setting up the trends. So yeah, it's the aviation kind of oil space is an interesting one. It's one that we'll keep doing work in, and yeah, it was pretty interesting. So I'd like to thank a few people. I'd like to thank Gwen O'Sullivan, who unfortunately couldn't make it here for this trip. She was planning on it. I'd like to thank some lab members of the lab that we work in. Caleb Marks is here. Emily Carroll is also around. And some research assistants that help with some of this work this summer, namely Kelsey Barrett and Sam Newman. And then finally, I'd like to thank the organizing committee of this conference. It was really, really great to be able to come here and present. Thank you.